So please join me and give a very warm welcome to Johan Rockström.
Thank you so much, Franz and Pavel. It's a great honor to be here in this fantastic hall, which is not only an awesome palace, but it's appropriate that it's been associated with so dramatic tipping points, because part of my lecture will actually be about tipping points. And it's the scientific story about a transformation into a completely new logic for human development on planet Earth. It really is the empirical evidence that we are at a juncture where we now need to change the logic into a completely new avenue for future prosperity. And it really starts with what I would argue is the most important scientific message to humanity, the empirical evidence that we've now become our own geological epoch. We, 7.2 billion people, multiplied by the industrial metabolism we represent, are now the largest force of change at the planetary scale. For the first time, we can say that we're actually hitting the ceiling of the biophysical processes that regulates the stability of the Earth system. To my students, I tend to say that whether we like it or not, we are facing a future where we need to relate and navigate a 369 world. In fact, I recently had to revise that. We're actually navigating a 4610 world. On average, we're moving towards a pathway which would lead us to an average temperature rise of 4 degrees Celsius, a place we haven't been for the past 4 or 5 million years. We are in the 6th mass extinction of species on Earth, the first to be caused by another species, and we're facing on average a future with 10 billion people, co-citizens, everyone with a right to development. That's the world of the Anthropocene. In fact, in this week's prestigious journal Nature, there's a whole issue around the Anthropocene, showing the latest work in the International Commission on Stratigraphy, now where the geologists are looking at when will we have the start date of the Anthropocene. It might be 8,000 years back when we started to domesticate animals and plants. Most likely it may be with the first nuclear tests in 1945. Myself, Will Steffen and others have argued that the starting point is probably in the mid-1950s when the great acceleration started, which I'll be pointing out. But this is really at the center stage of science today, ripping down all the old signboards that we all learned from school, you know, when we were taught that we were in the Holocene. Now, dear friends, welcome to the Anthropocene. Now, the summary, therefore, of the new juncture is that there is a new global context. We're welcoming humanity to the Anthropocene. That actually is coupled to new risks of tipping points in the Earth system, which I'll be going through. But it also leads to something very humbling, that if we're facing these very large, unexpected risks at the planetary scale, there's equal amount of science today to say that the desired state of the planet is the Holocene, the last 10,000 years of remarkably stable conditions, which I'll call the Eden's Garden for human prosperity on Earth. And these three insights, that we're now the biggest pressure, that in fact we cannot exclude non-linear catastrophic changes, and that the Holocene is our desired state, is what leads to the recognition that we need a great transformation. But the drama, but also the beauty of this, is not a transformation back to the caves. It's actually increasingly based on the evidence we have of a second machine age, of disruptive technologies, enormous opportunities and breakthroughs in renewable energy systems and sustainable food systems, an agenda which I will call abundance within planetary boundaries. The new storyline of growth, economic development for all within a safe operating space on Earth. So off we go. Is this something that is recognized, that we're actually facing this new situation? Well, absolutely yes. This is the famous global risk report coming out each year of the World Economic Forum. It's the messy graph of how over 2,000 CEOs in the world perceive risk for their businesses. And of course, you have the risks we all talk about and read about in Wall Street Journal, etc., about fiscal crisis, regulatory failures, governance failures. But look at the dots down here. Here we have a recognition that infectious diseases, water security, food security, climate change, biodiversity loss are equally understood today as being fundamental for the success of business and world economic development. We're starting to recognize that leaders in the world see the interconnectedness between the social, the financial, and the ecological. Just this week, or last week, in the prestigious journal Proceedings of the National Academy of Sciences, colleagues of Jeff at the Earth Institute and others showed something absolutely remarkable. 4 years before the break of the catastrophic war in Syria, the most devastating drought ever recorded, probably the worst drought since the Mesopotamian agricultural revolution in the crescent of Iraq, Iran, 8,000 years back, hit Syria, leading to over 2 million people leaving rural areas into cities in the run-up to the civil war. Now, nobody can really make clear the causality here, but this is empirical evidence of something new that we haven't seen before, of abrupt turbulence from the Earth system, in this case of climate-induced unprecedented droughts, coupling with social instability. You may be aware that the same story can be told of the Arab Spring, because just prior to the Arab Spring, you had a few years of remarkable increases in food prices, which led to food riots in cities like Tunis and Cairo. These were caused by a 350% rise in phosphorus prices, the key fertilizer in modern agriculture, unprecedented forest fires in Russia, which meant that President Putin stopped and shut down the export borders of staple foods, and at the same time, Prime Minister Rudd in Australia shut down the export borders in Australia after 12 years of unprecedented droughts. So we had suddenly a global turbulence on the world food market, which hit right at the same time of this uprising of a new generation of socially connected youth that were rising against 40 years of dictatorial rule. Perhaps the first example of social ecological turbulence hitting at a regional scale, destabilizing entire nations. This is the evidence, putative, but though the evidence of the Anthropocene. Why are we in this situation? Well, that is also today very established, well established. It is the evidence, empirical observations of the great acceleration of increase in human pressures. This is the latest update coming from the Global Environmental Change research community and the International Geobiosphere Program, supported very much from IASA and other colleagues, showing on the left-hand side the drivers of change in the world, and the right-hand side, the impacts on the Earth system. And what you're seeing here is the same pattern of exponential rise, which looks I should go back here which looks the same right across this period, which is from the Industrial Revolution all the way till today. These impacts, by the way, have sister impacts when it comes to health-related dynamics. We tend to forget that social, economic drivers of exponential change results in exponential negative environmental impacts. But then you have the remarkable rise in non-communicable diseases, the rapid exponential rise in different forms of antibiotic resistance. So these exponential curves of change is a feature of the Anthropocene. And I just want to go through very quickly to show you how these look like, because these are empirical observations. This is not models or hypotheses. This is from the Industrial Revolution until today, how the drivers of change have shifted. And just look at the pattern of the curve on energy use, world population, urban population, GDP growth, direct investments, dams, the large dams that has made modern agriculture possible, water extractions, paper production, fertilizer consumption, transportation, telecommunications, tourism exponentially rising, which then gives impacts in the Earth system with the rise of carbon dioxide. The only hockey stick we normally talk about at the planetary scale, but you can pick any parameter in the Earth system that matters for human well-being. It looks like this one. I go through a few. Methane release from modern agriculture, nitrous oxide from air pollution, surface temperatures, depletion of stratospheric ozone layer, which was one of the disastrous risks we faced in the 1980s, overfishing of the oceans, ocean acidification, nitrogen overload and eutrophication, shrimp agriculture increase, deforestation, one of the very important regulating factors of resilience on the Earth system, land expansion, and here's the one that makes me most nervous, the exponential rise of the richness of species on Earth. So the drama is we have this pattern on everything that matters for our own future. Up until the mid-1950s, we actually had very limited impacts on the Earth system. In fact, we were, to speak in very simple language, a relatively small world on a large planet. In fact, it was quite simple. Even unsustainable growth worked. It wasn't a surprise that we so successfully embarked on a GDP-based growth paradigm because the planet was our best friend, Earth system was so incredibly forgiving. There was ample atmosphere, a lot of forest to deforest, huge amounts of surplus of fish in the oceans. We could abuse with no invoices coming back to the Earth system. Despite this, the warnings came early. Rachel Carson wrote her Silent Spring in 1962, an early warning of the risks of the modern industrial chemical-based industry. The Limits to Growth report came 1972, warning that if we followed a path of exponential rise of pressures, the world economy could be hit by 2020. Well, you all know what happened with these dots there. They were shot down by conventional economists and policymakers very effectively. Now, that is inexcusable, but I would argue that if we look at this curve, one could perhaps forgive them because we were so early in the rise. Actually, Rachel Carson was a visionary person who warned much, much before the empirical evidence. But dear friends, now we're up here. Now we're standing on the mountain of knowledge, of exponential rise on any parameter that you can pick that matters for our own economic development, and it looks the same. So the conclusion is that now we are the first generation to know that action is actually absolutely needed, and that that need is unequivocal. This is a very new situation compared to where we were just 40, 50 years back. The second thing, which is actually equally important to recognize, is that, so we would argue that the Anthropocene starts in the mid-1950s with the Great Acceleration. But did the Earth system start hitting back at that point? Oh no. The Earth system continued to apply its resilience and dampen and help us. Up to when? Well, up to quite precisely 1989. It's in 1990 that we passed the first boundary limits with regards to concentration of greenhouse gases. It's at 1991 that the cod fisheries outside of Newfoundland surprisingly collapses and does not recover. The Baltic Sea tips over in 1991 as well. In 1992-93, we see the first cases of nonlinear dynamics in many of the tropical coral reef systems in the world. We start to see that it's in the 1990s onwards that the Earth system starts sending invoices back to the world economy. It's just in the last 10 years we start seeing the big numbers of costs with regards to unexpected shocks to the system. The $20 billion costs of Sandy hitting right into Manhattan, for example. So the situation is quite remarkable. It's just over the last 25 years that we enter the really saturated phase of the Great Acceleration. And that's why 2015 is such a decisive year. It is an era of new global risks. And I'll just go through those very briefly. And I just find this to be perhaps the most important way of understanding what we're doing to our own planet. This is ice core data of the past 2,000 years. It's a very good way of showing how incredibly limited the temperature variability was on Earth. You cannot see the y-axis perhaps, but it's a plus minus 1 degree Celsius variability during this period. We are on a journey to 4 degrees. We're moving many, many magnitudes outside of the variability domain of a safe future. In fact, the IPCC shows this in a very, very effective way today, but also in a way that makes me very nervous. Because what I'll show you here is that the more we learn of how the Earth system behaves under climate pressure, the more nervous we become. Okay, so what you have here may look a bit complicated, but it's actually quite simple. You have the 3 latest assessment reports of the Intergovernmental Panel on Climate Change, 2001, 2007, and the latest one in 2013. What you have here is the famous red embers diagram that Naki and others here have been part of producing. And I'd just like you to focus on this absolutely lowest column here, which is the risk of so-called large-scale discontinuities. To put it simple, climate-induced catastrophes. Now, in the 2001 report, if you just look at this column, you see that the estimate was that that could occur at roughly 4 to 5 degrees warming. That was the evidence in 2001. And then we learned more and more about the interactions and complexities of Earth resilience. And in 2007, the risk of large-scale discontinuities is down to 3-4 degrees. And finally, we come to the recent report, and we see that the risk of inducing irreversible large-scale changes is down to 2-3 degrees. So please, dear friends, never get cheated when people tell you that scientific uncertainty means we cannot act. Scientific uncertainty will always be there, but the trend line in terms of risk is absolutely clear. The more we learn, the more we recognize the humble fact that the Earth system is a sensitive, but self-regulating, complex system which has been our friend for many, many centuries and is now coming to a point of saturation. This is a very different situation to be in. Let me just illustrate that in a very dramatic way. So the IPCC is the consensus among thousands of scientists. It's a conservative analysis. It can be criticized for underestimating risks. Now let me give you this example from the IPCC. Where are we today in terms of concentration of greenhouse gases? We are actually, believe it or not, at 450 ppm for all greenhouse gases in 2015. Actually, the boundary that we promised not to surpass in Copenhagen. What's the probability, according to IPCC, of reaching catastrophic warming in the world? And I picked 2 degrees here, 4 degrees and 6 degrees. Let's take 6 degrees. I take 6 degrees because it's so high and so obviously catastrophic that even a climate skeptic would agree that we don't want to be there. Okay? So let's take 6 degrees. What's the probability at current concentration of greenhouse gases that we would reach on the long term 6 degrees? And according to IPCC, that probability is 1.6%, according to a conservative analysis. Now, what does 1.6% mean for a catastrophic outcome? Well, if you talk to reinsurance people in companies like Munich Re and Swiss Re, they say, we don't issue insurances at percentage levels of catastrophic risk. We operate at promille level. In fact, a 1.6 probability is the equivalent of us accepting 1,500 fatal aircraft accidents every day. So this is a probability level that we would never accept in any other sector of society. But when it comes to our own life support systems on Earth, we put our heads in the sand and do not recognize these risks. This is the situation of the Anthropocene today. Now, why is it that we have these risks? Well, it comes to systems like this. This is a picture of a healthy Svalbard in the Arctic. This is how we want the polar regions to be, permanent white ice sheets. We're seeing accelerated melting in both poles, particularly of Arctic sea ice. That has dramatic impacts on biodiversity in local communities. But in particular, what happens is, illustrated in this picture, you see a shift in color. You see a darkening of surface because you have a liquid surface. That is called a change in albedo, which means that you get a self-reinforced warming because instead of reflecting back 90% of incoming heat from the sun to space, a much, much larger portion is sucked up as energy. This is, to put it simple, the scientific nightmare. That so-called negative feedbacks, when the Earth system dampens and cools, shifts over into positive feedbacks of self-reinforcing change. Planet going from friend to foe. Do we have evidence of this occurring? Unfortunately, yes. I would argue that this is probably the most important scientific graph over the past few years. Sorry, dear colleagues who have produced fantastic graphs and tables over the past years. Because this is satellite data from NASA over Greenland. It shows on the y-axis the reflectivity of incoming solar radiation back to space. As I mentioned earlier, the colored lines is how we want things to go from January up until December. Roughly 90% is reflected back. It goes down a bit over summer because naturally the fringes of Greenland is melting, so you get a liquid surface. And then suddenly, in an unprecedented hit, 2012 is the black line. To everyone's surprise, it goes through the floor, and for the first time in observed history, Greenland goes from being a net cooling system for the planet to become a net warming system. The entire surface of the Greenland ice sheet is melting. Just that little film with a slight darker color. And Jason Boxen, scientist at the Barrett Institute, has calculated this 2-week period in July corresponds to an increased injection of roughly 100 exajoules of heat into the atmosphere. Over the period 2000 to 2012, just the shift gradually toward this point corresponds to over 400 exajoules of new energy into the atmosphere. Now that's a huge number. So just to give you the parity of what it means, the global energy consumption of primary energy is roughly 500 exajoules. The US uses roughly 200 exajoules. It means, to put it again in simple language, that little Denmark steps forward momentarily as the largest climate-forcing nation on Earth, bypassing China and the US. Not because the Danes emit so much greenhouse gases, but because the Earth system changes feedbacks. So this is what we have to be humbly aware of, that the Earth system is sensitive. We were in the scientific community absolutely shocked in May 2014 when 2 independent research teams showed something that we had hoped not to happen. We've always thought that the Antarctic is more resilient and Arctic is more sensitive, but observations now show that that may be a mistake. we see irreversible sliding of certain glaciers in the West Antarctic ice sheet, in particular the Thwaites Glacier, that seems now to be irreversibly gliding into the ocean, not because of melting from above, but because of warming from below, lubricating the fact that this is ice standing on sloping bedrock. Now, the drama is that this glacier is like a plug holding upstream glaciers. So when that one starts moving, we see irreversible risks of other glaciers moving. In fact, the conclusion in this study, believe it or not, is that this probably means that we've crossed the tipping point, irreversibly committing ourselves to another 1 meter sea level rise this century. Now, the IPCC has already put 1 meter on the table, so it would mean 1 + 1 this century, 2 meters. And I would argue that is putting us in a situation that in many cases is beyond adaptation. Same goes for methane release. Increasingly, science showing that in the Siberian, Arctic, East Arctic shelf, we're starting to see puffs of methane be released from thawing permafrost of subsurface coastal regions, to a point that it's been even costed to potentially be another invoice to the Earth system in the order of $70 billion. These are large impacts of changes in feedbacks. We see it in the tropical marine systems tipping over from desired states to permanent undesired states. We see much, much more evidence now being put forward in these kind of analyses, which are absolutely fantastic from a scientific perspective to humanity, showing the systems in the Earth system that could tip over abruptly and go from these dampening to self-reinforcing systems. This is the famous tipping elements by Tim Lenton and John Schellenhuber. So to summarize the risk story, and I promise I'll now go from the negative to the positive, we are in a situation where two giants are colliding. The first giant is the right to development among 9-10 billion people, where we actually are moving very positive to a point where we don't have 1.5 billion rich co-citizens on Earth, but rather 5-6 billion people who all have not only right to development, but moving decisively towards lifestyles that are in parity with us in this room. But the second giant is that the Earth system is now showing evidence of nonlinear changes. And this is something we need to relate to, and that is what takes us to the question, what do we do then? How do we relate to this? How do we actually navigate a future while maintaining resilience in the Earth system? So to answer that question, we have to start by answering this question. If we are pushing so much pressure on the planet, what is the desired state of our own planet? Are we leaving Eden's garden? And science can actually answer this question. And again, it comes from ice core data, this time from Greenland. And this is ice core data where the y-axis shows temperature variability, a good proxy of how it was to live on Earth. And it's an interesting period, in fact decisive. It's the last 100,000 years. It's picked precisely because we've been modern humans during this entire period. And as you can see, we had a very jumpy ride indeed during most of this period. We were hunters and gatherers. We were a few million people. In fact, during this very cold point, right here, when sea levels were 70 meters lower than today, when fresh water was tied up as ice in the poles, new data shows that we were down to less than 15,000 fertile adults on Earth. We were virtually extinct. We were at a bottleneck because we were hiding in the high lands of Ethiopia, the only place left where there was some fresh water and biomass, virtually extinct, meaning, by the way, that we're very close relatives, all of us in this room. Jumping along up until the point when we exit the last glacial era and enter in the red circle what we've learned to call the Holocene, the remarkable, stable era of stability on planet Earth. And what do we do when we enter the Holocene? Well, we barely enter it, and we do the most important invention of all. We go from hunters and gatherers, we become farmers. And we invent agriculture not in one place, but actually in at least 4 places simultaneously on Earth. And this is a proof that something very important happened. Because what happened is that the temperature variability became so low. Everything we nurture and love and depend on in nature settles in. The genetic diversity has been there for 100 millions of years. But you know, the grasslands, the wetlands, the rainforests, the savannas, the rainy seasons, the predictability year after year, suddenly people realize, oh my God, 15th of May, it seems that it's warm enough in the northern hemisphere and I have 100 days to cultivate. Or the rainy seasons start predictably in a certain point year after year after year. So we domesticate animals and plants in 4 different places at least. And because we didn't have smartphones or any emailing to each other, it's a proof that we had this knowledge for a long time, but we took it because we had so predictable, stable conditions on Earth. So the message, which is as simple as dramatic from science, is that the Holocene is the only state we know of planet Earth that can support the modern civilization as we know it. We've lived outside of the Holocene, but we know of no other state that can support our modern world in an ethically responsible way. Now that's a very dramatic statement, but it's also such a useful statement because we know the Holocene so well. We know the hydrological cycle, the carbon cycle, the nitrogen cycle, the phosphorus cycle. We understand the stratosphere, the cryosphere, the atmosphere, the biosphere. So it enables us to have that as a reference point. And if we take that as a reference point, the next question becomes, well, so if the Holocene is our desired state, what does it take to remain there? What does it take to have human prosperity within a safe operating space? And that's what Pavel referred to when we gathered leading global environmental change scientists over a 2-year period to ask 2 questions. 1, what are the Earth system processes that we need to, that regulates the stability and resilience of a planet? And secondly, for each one of those, can we actually quantify a boundary along a control variable beyond which we enter a terrain where science shows evidence of changes in feedbacks and potential catastrophic tipping points. And that led to the Planetary Boundary Framework, which was published first time in 2009, and the 5-year update came out in Science just a month back, 2 months back now. And this is, well, I'll just go through very briefly what it meant. We illustrated it in this way, which shows the 9 boundary processes that we proposed in 2009. A few of these are so to say obvious for everyone in this room. The climate system, the stratospheric ozone layer, ocean acidification, the big systems that we know have planetary scale tipping points. Less obvious perhaps is that we have 4 boundaries that regulate the Earth system under the hood: biodiversity loss, land use change, interference with the global hydrological cycle, and interference with the big cycles of nitrogen and phosphorus. We have so much evidence that these systems may not have tipping points at the planetary scale, but they regulate the stability of the Earth system from below. But then we also believe that chemical pollution and aerosol loading, which is air pollution to put it simple, because it affects, for example, the large rainfall systems at the regional scale, are candidates for planetary boundaries, but we couldn't quantify them in 2009. By quantifying, though, the boundaries where we could quantify, it gives us in green a safe operating space. And it enables us to estimate, which has been done here in 2009, where we are with regards to these boundaries. And we concluded at the time that we had transgressed 3 of the boundaries: biodiversity, climate change, and nitrogen. And I want to emphasize something really important, that this framework did not come out of the blue. It was the incremental natural next step from massive advancements in Earth system science over decades. It builds on the guardrail research, carrying capacity research, tipping elements research, the global Earth system dynamics modeling research. So the Planetary Boundary Framework is really an incremental natural step in the trajectory of science. The 5-year update then is shown in numbers here. I'll now go through this in detail. It's simply just to remind me to tell you the following. 2 things happened over the last 5 years. One is that there has been a remarkable critique and update and improvement of the Planetary Boundary Framework. I mean, an enormous amount of publications coming out specifically around this framework. And the interesting thing when we did the update and scanned off all this science is that nobody is suggesting a 10th boundary, but nobody is arguing that we got one of the 9 wrong. So it seems we've got it right, that these 9 processes, if we can manage those in a sustainable way, we have a very high likelihood of a prosperous future for humanity. That's very reassuring for science, a 5-year review period, and we come back to the same 9. The second very important thing is that we've improved the quantifications of essentially all of them. So for example, on climate, we've narrowed in even further the uncertainty range, and we say that the boundary is today at 350 ppm for carbon dioxide. On biosphere integrity, the biodiversity boundary, we've made a major breakthrough in not only counting the number of species in terms of extinction rate, but also the role species play in building resilience and providing human well-being. We have made major improvements on the nitrogen and phosphorus boundaries, including both freshwater and ocean tipping points, and also being much more clever in the nitrogen boundary. We've changed the land use boundary entirely, from cropland to looking at what's the minimum size of forest systems we need to maintain to regulate the stability on Earth, and even giving numbers for that. And finally, on freshwater, we've been able to take the global freshwater boundary all the way down to the minimum amount of freshwater we need to maintain in all the river basins in the world. So it's a much more robust analysis building on the great advancements in science over the past 5 years. So I would say we're quite reassured when we now present this graph, which is the update of the state today, showing unfortunately that we actually are in a danger zone on both phosphorus and nitrogen, and that we actually have entered an uncertainty range on land use. It's important to recognize here that when you're in the yellow, you're in the scientific uncertainty range. We don't know what is happening there. And in red, we have a high likelihood, a lot of evidence that things can go wrong. It's not as if the world kind of topples out of its stability domain just because one process is in the red, but it shows a warning sign that things can go wrong over the next, so say, century if we do not veer back into safe operating space. Now, here I just show you why the systems interact so intimately. So here's just the story why we have both the climate system with big tipping points, but also the biosphere systems. Here's our emission of greenhouse gases since the Industrial Revolution, which adds up to 545 billion tons of carbon, or 545 units. Now, you may ask, is it that amount of carbon dioxide that has led to 1 degree warming so far? Well, as we know, that's not the case. It's actually just half of it that remains in the atmosphere, and a remarkable 55% has been taken up by the oceans and terrestrial ecosystems, the world's largest subsidy to the world economy. Now, this is a proof why we need to take care of both the land boundary, the ocean boundary, to have a safe climate future. We need to think in integrated ways to have a safe future. The planetary boundary analysis also allows us to do the following, to just show the journey since the Industrial Revolution. So this is now in 1750. We're right in the middle of this safe operating space. We have actually not, kind of exploited any part of the safe operating space. Already in the 1950s, we start to eat portions of the safe operating space. We're actually in the red already on land use change because of the modern agricultural development and expansion of agricultural land, now covering 40% of the biosphere. 1970, we expand a little bit further, but still have ample space. As I mentioned earlier, there's a lot of room in the planet. But look at 1990. We're right in the red on depleting the stratospheric ozone layer due to the chlorofluorocarbons in our cooling and heating systems. But look at this remarkable thing that happened then. Science warned about this. Policy took notice. The world gathered and signed the Montreal Protocol in 1987. And the current situation is we got back into the safe operating space on one of the 9 boundaries. So this is an example that we have been planetary stewards in the past, and that we probably have a good chance of being it again on the boundaries where we're now in a danger zone. Now, what does this all imply to close on sustainable development? Well, I would argue it has profound implications. We've learned to think of sustainable development in the following way. The seminal work by the Brundtland Commission in terms of the social, economic, and environmental pillars of sustainable development. We must probably just recognize that this paradigm has not served us so well in the Anthropocene and has led to what we can call a Mickey Mouse economy, where the economy has grown at the expense of natural and social capital. What the planetary boundary analysis suggests is that we may have to think of a new paradigm where we have economic growth, where we have abundance and development within a safe operating space on Earth, which I will argue, and I think Jeff will refer to it, increasingly it is understood also by world leaders. And the interesting thing is that being outside of the safe operating space is, of course, a warning sign, but there's so much evidence that we can veer back into a safe operating space. And there are 2 big transformations we need to succeed with. And the first one is clearly a transformation into a fossil fuel-free or a decarbonized world economy. And the great work by IASA and multiple colleagues show in the Global Energy Assessment that that transition is feasible. We can return back into a safe operating space on energy. It is proven increasingly by the exponential rise of renewable energy in the world. These are curves showing for several countries in the world the rise in solar and wind, which is a remarkable journey where we now have grid parity on many of these systems in large parts of modern markets. The second large transition is clearly a transformation into a sustainable food system in the world. Now, analysis like this one by John Foley and colleagues show that we can feed humanity on current land, also through sustainable means. There is a possibility of veering back into a safe operating space on both food and energy. Now, the business community is understanding this increasingly. Björn Stigson is here, the former head of the World Business Council. The World Business Council has actually taken the Planetary Boundary Framework and translated it quantitatively into what they call an Action 2020 list, where the boundaries are quantified as guidelines for big companies. The World Business Council represents 200 of the world's largest companies. This is interesting. They do it not as a corporate social responsibility agenda, but really as a means of strategic risk minimization and business success in the future. Japan is moving very rapidly out of nuclear, as you're all aware, into different forms of renewable energy at a pace which is absolutely astonishing. Analysis show that we can have a penetration up to 20-30% of the world economy with renewable solar systems just by mid-century. We can go to scale with very many of these technologies. We also know where the culprit is to a large extent, where we have a remarkable, even devastatingly unacceptable subsidy to fossil energy systems of a staggering $500 billion. If I remember right, Naki and others, the investment required for a successful transition into renewable energy systems was estimated roughly $1,500 billion, 3 times the subsidy for fossil fuel systems in the world. So we're seeing here a situation of a mismatch where small tweaking can lead us very rapidly in the right direction. So to close then and summarize, we live in a world that still largely believes that we can have growth without limits. We scientists, I have to be self-critical, have probably, a bit like Moses walking 40 years in the desert, been preaching limits to growth a bit too far and unsuccessful. Now there's a new story about growth within limits, a positive story of abundance and opportunity within a safe operating space for humanity on Earth, which is not a story of halting development. It's a story about prosperity based on innovation and transformations to a desired future. Is people across the world understanding this? I would argue yes. I think we are not only at a biophysical tipping point, we see social tipping points increasingly. When 500,000 people marched through Manhattan in September 2014 in the People's Climate March, it was a manifestation of something happening in the consciousness of people, seeing that the opportunity is so large of going towards a transformation to a sustainable future on a stable planet. And that's very promising this decisive year 2015. Thank you very much.